Across the darkness of space, where light itself takes minutes, hours, even years to reach distant worlds, we find ourselves suspended in a cosmic ocean far grander than anything we can truly comprehend. Each point of light in the night sky is not just a destination, but a clock, silently marking the distance between human curiosity and the great unknown. Tonight, we will drift beyond Earth and journey across millions, even billions of miles, tracing the silent pathways through space and time. How long would it truly take to stand beneath Venus's golden clouds or witness the storms of Jupiter with your own eyes? What about Neptune, where a single day is longer than our imaginations dare to stretch? If you enjoy these journeys through time and wonder, please like this video and subscribe to help us travel even farther together. Now, settle in, let your imagination lift, and let us drift gently outward into the waiting dark. Let's begin. In the silence after launch, Earth begins to fall away beneath us, not as a planet, but as a memory. The roar of engines becomes distant, replaced by the deep hum of space itself. Time slows. Our journey begins not with motion, but with transformation, from earthbound to cosmic. From the moment ignition begins, the world we have always known starts to recede into the background of consciousness. The metal hull trembles, the force of millions of pounds of thrust pushes us upward. And in that ascent, we are no longer citizens of a planet, we are travelers of the void. As gravity loosens its grasp, Earth's familiar features, oceans, mountain ranges, swirling clouds, collapse into a single breathtaking view. It is here, in this narrowing perspective, that we experience the first shift in time. Seconds stretch. Thoughts deepen. A profound stillness settles in our minds, as if the universe itself is taking a gentle breath before revealing its secrets. As the spacecraft crosses the Kármán line, the invisible boundary between Earth and space, everything changes. The pressure of the atmosphere vanishes. The sky, once a gradient of blues, transforms into velvet darkness. There is no sunrise, no sunset, only a slow turning of the planet beneath us. Every rotation, every shadow stretching across continents, becomes a reminder of how quickly life moves down below, and how slowly time seems to drift up here. The hum of instruments replaces the sound of wind. Motion is now defined not by footsteps or wheels, but by orbit, by momentum, by gravitational pulls that extend far beyond anything we have felt on Earth. The journey ahead is not merely about distance, it is about shedding layers of everything human. The need for solid ground, the sense of up and down, the idea that time flows steadily forward. Here, time becomes elastic. It stretches with each mile covered, each landmark passed, from low Earth orbit to the edge of the planet's gravitational influence. We begin to understand that space is not empty, but filled with invisible forces. Gravity pulls, light bends, even time itself, like an ancient traveller, moves differently in these regions. As we complete our first orbit, Earth shines below us, serene and fragile. The cities that once seemed huge now appear as pinpricks of light scattered across the night side of the globe. The storms that once dominated our weather systems become slow spirals drifting across continents. From this vantage point, borders vanish, nations disappear. There is only one living world, turning patiently beneath the vastness of space. And with this realization comes the first hint of cosmic humility. Humanity has always been a spacefaring species. We have simply been waiting for the technology to remember. As our spacecraft aligns for transorbital injection, preparing to depart Earth's gravity well for the broader solar system, we feel the last tug of home. It is not just gravitational, it is emotional. The knowledge that every second moving forward will place greater distance between us and everything we have ever known. Yet, there is also peace in this moment. The peace of purpose. The peace of curiosity. Beyond Earth lies a celestial path, carved over billions of years by the motions of planets and stars. We are not creating this journey, we are following it. With the engines firing once more, we are no longer orbiting Earth. we are leaving it. In this moment, our calendars no longer follow days, but distances. Our clocks no longer mark hours, but trajectories. And as the last glimmer of Earth's atmosphere fades into the eternal night, we finally understand we have not lost our home. We carry it with us as a memory, a beacon, and a promise that every mile traveled is a step toward understanding not just where we are in the universe, but who we are. Our voyage has begun. Beyond the atmosphere lies a realm without resistance, where motion continues endlessly and gravity reshapes our path. Here, travel time is measured not in miles but in velocity and slingshots, as planets themselves become stepping stones through time. In space, there are no highways like on Earth, no mapped-out roads or visible trails to follow. Instead, we are guided by forces older than time itself: gravity, momentum, and orbital geometry. These invisible currents form pathways that spacecraft must carefully navigate, using the subtle pull of planets to accelerate, redirect, and propel themselves forward. The true art of interplanetary travel is not brute force, but balance. We do not fight against gravity, we use it as an ally, allowing it to shape our journey like wind fills the sails of a ship crossing a cosmic ocean. These gravity pathways, called transfer orbits, follow precise mathematical arcs that connect one planet to the next. They are not chosen for convenience, but for efficiency. A spacecraft cannot simply fire its engines in a straight line through space. It must fall toward its destination, riding the curves in spacetime carved by planetary mass. Earth's gravity holds us in its embrace until we reach what scientists call escape velocity, about 11 kilometers per second. Once this threshold is crossed, we are no longer bound to Earth. We become wanderers on the solar wind, carried not by fuel, but by the elegant physics of momentum. Here in the vacuum, motion is persistence. Without air resistance, every small push carries on forever, unless interrupted by another force. A single burst of propulsion can send a spacecraft coasting for months or years. Every moment becomes a careful trade between time and energy. Go faster, and you must use more fuel. Conserve fuel, and you must accept that time, days, weeks, years, will stretch into the great expanse ahead. The planets themselves become celestial rest stops along our journey. Their massive gravitational fields act as cosmic slingshots, accelerating our spacecraft without using a single drop of fuel. This technique, known as a gravity assist, is both a scientific marvel and a poetic dance. As we approach a planet, we fall into its gravity. As we swing past, we steal just a fraction of the planet's orbital momentum, using it to slingshot outward at higher speed. In exchange, the planet loses an immeasurably small amount of its own motion, tiny but real, proving that even on an interplanetary scale, nothing in the universe is free. These invisible highways are not always open. They exist only in narrow windows of alignment, when two planets orbit into the correct positions relative to each other. Launch too early or too late, and the pathway closes. We would have to travel a longer, slower arc, wasting precious time. In space, timing is everything. Mission planners sometimes spend decades waiting for a perfect moment, a moment when Earth, Mars, Jupiter, and Saturn align like stepping stones stretched across cosmic waters. As we travel along these gravitational lanes, we are reminded that the universe is not empty. It is a web of forces, each pulling on the other, each shaping the future of everything in motion. Space is not a void to be crossed. It is a living landscape, constantly shifting, flowing, and guiding us through pathways that cannot be seen, only felt. And so we continue, eyes fixed not on where we are, but on where gravity will take us next. For to travel through space is not simply to move, it is to surrender, gently, to the silent architecture of the universe itself. Mercury waits in the inner dark, a world so close to the sun that dawn arrives like a blade of white fire. To reach it, we don't speed up, we surrender speed, falling inward along a curve of light. The question isn't only how far Mercury is, but how slowly we can learn to arrive. From Earth's orbit, every instinct says, go faster. But the inner solar system teaches a subtler lesson. To reach Mercury, we must shed energy. Earth circles the Sun at about 30 kilometers per second, Mercury whips around it at roughly 47. As we drop sunward, our heliocentric speed naturally rises, so the real challenge isn't getting to Mercury, it's arriving slow enough to stay. That is why missions to this small, scorched world use elaborate dances of flybys and gravity assists, shaving speed with each pass until capture becomes possible. The fastest way to simply touch Mercury is a direct transfer for a flyby, historically on the order of 3 to 5 months. Mariner 10 proved this in the 1970s, taking about 4.5 months from launch to its first Mercury encounter. But orbiting Mercury, truly lingering there, demands patience. NASA's Messenger spacecraft launched in 2004, looped past Earth once, Venus twice, and Mercury 3 times, finally easing into orbit in 2011, about 6.5 years after departure. Europe and Japan's Bepi Colombo followed a similarly intricate path. 1 Earth flyby, 2 at Venus, then multiple at Mercury, spending years trimming speed before planned orbital insertion in the mid-2020s. Inward is not closer. Inward is harder. Approach becomes an exercise in serenity. Each flyby is a metronome tick in a long composition, a precise brush with a planet's gravity, a quiet course correction, an incremental surrender of energy. Between encounters, the spacecraft coasts through radiant silence, the sun growing larger, harsher, more insistent. Thermal shields become lifelines. Sunlight here is up to 10 times stronger than what warms Earth. Guidance, navigation, and control systems practice a form of celestial Tai Chi. Small gestures, enormous consequences. And then, Mercury fills the window. A charcoal grey world, cratered and ancient, framed by a solar glare so fierce it turns space to glass. Temperatures swing from searing to cryogenic, up to 430 degrees Celsius, 800 degrees Fahrenheit. At noon, plunging below -170 degrees Celsius, -290 degrees Fahrenheit at night. With almost no atmosphere, only a fragile exosphere of atoms knocked loose by sunlight and micrometeorites, there is no wind, no weather, no softening haze. Shadows carve knife-edged boundaries. The sky is always black. Time on Mercury feels inside out. A year lasts only 88 Earth days, yet one solar day, from noon to noon, takes 176 Earth days. Stand on the surface near the terminator, and you could watch the sun creep, hesitate, even seem to reverse near perihelion, a strange ballet born of orbital resonance and rotation. Here, dawn is a geologic event. Scientifically, Mercury is a paradox wrapped in extremes. An outsized iron core, a global magnetic field in a world so small, a surface scarred by volcanic plains and tectonic cliffs, lobate scarps, that reveal a planet still shrinking as it cools. Each orbit maps a chapter of planetary formation, written in metal and light. How long does it take to reach Mercury? For a flyby, mere months. For an orbit, years, patient years spent peeling away speed, layer by careful layer. The reward for that patience is a vantage point unlike any other in the solar system, the innermost keep of our star, where space, heat, and time are distilled to their elemental forms. And in that stark brilliance, Mercury offers a final lesson. Sometimes the shortest distance demands the longest grace. Venus glows like a lantern in the dawn sky, closer to us than any other planet, yet reaching it means descending into a world of crushing heat and eternal storms. How long would it take to glide through its clouds and witness a sunrise that never ends? From the surface of Earth, Venus appears serene, soft, radiant, almost gentle in its beauty. Ancient astronomers named it after the goddess of love, enchanted by its steady brilliance. Yet behind that golden glow lies a planet so extreme that it challenges every expectation we have about habitability, atmospheric pressure, and time itself. To reach Venus, we must first understand that we are not simply traveling to a neighboring world. We are diving inward, toward the furnace of the sun, falling toward a planet that spins to a different rhythm than any other in the solar system. Although Venus is Earth's closest planetary neighbor, Reaching it is not as simple as pointing a spacecraft directly at it. Because Venus orbits closer to the Sun, we must first reduce our orbital speed around the Sun, essentially falling inward. This takes more energy than travelling outward to Mars. We must carefully time our launch to match Venus's orbital window, which opens roughly every 19 months. When the alignment is perfect, a spacecraft travelling on a Hohmann transfer orbit can reach Venus in about 120 to 150 days. Just 4 to 5 months of drifting across the void, watching the Sun grow larger with each passing day. During the journey, the spacecraft is slowly captured by the Sun's gravity, accelerating as it draws closer to the inner solar system. Temperatures rise, radiation levels increase, and our destination grows brighter, transforming from a distant star-like object to a world veiled in thick clouds that reflect nearly all sunlight back into space. This is why Venus shines so brilliantly. It is not a mirror, yet it reflects more light than any other planet, glowing like a cosmic beacon in the early morning and evening skies. Approaching Venus is like approaching a dream wrapped in mystery. There are no shadows here, only a constant blanket of light filtered through the atmosphere. The planet rotates so slowly, taking 243 Earth days to complete a single rotation, that a single Venusian day is longer than its year. If you stood on its surface, the Sun would appear to rise in the west and set in the east, moving across the sky so slowly it would seem almost motionless. Imagine standing on a world where sunrise takes weeks, where time stretches so far that a single afternoon could last a month. Yet the beauty of Venus hides a punishing reality. Its atmosphere is composed almost entirely of carbon dioxide, trapping heat in an unstoppable greenhouse effect. The surface reaches temperatures of nearly 880 degrees Fahrenheit, hot enough to melt lead. The pressure is over 90 times that of Earth, equivalent to being nearly a mile beneath the ocean. Clouds of sulfuric acid swirl overhead, reflecting sunlight back into space even as they trap heat below. Once imagined as a lush jungle world, Venus is in truth a planetary cautionary tale. But while landing on Venus may be impossible for humans today, exploring its upper atmosphere could be our key to understanding planetary evolution. At about 50 kilometers above the surface, temperatures and pressures are remarkably Earth-like. It is here, in the golden haze, that future balloon-like habitats could drift peacefully above the inferno below, forever watching the horizon where sunset never truly ends. To reach Venus is not only to measure distance, it is to step into a mirror of Earth's past and a warning of its possible future. The journey there may take only months, but the revelations it offers could span centuries of human understanding. Though Venus is Earth's sister in size, its atmosphere is a furnace of carbon dioxide. As we approach, we measure our journey not just in distance, but in the unfolding history of a planet that became a warning. Earth and Venus were born beside each other, sculpted from the same primordial dust that circled the infant sun. In their earliest days, they may have glimmered with oceans, clouds, and the building blocks of life. But where Earth calmed, cooled, and nurtured life, Venus spiraled into catastrophe. As we descend toward Venus, our spacecraft becomes a time machine, tracing the divergent paths of two planetary siblings, one that chose balance and one consumed by runaway transformation. The deeper we go, the more Venus reveals not just its nature, but the delicate fragility of habitability itself. From orbit, Venus looks peaceful, its creamy clouds slowly churning in a perpetual global blanket. Yet beneath that facade lies a world of relentless turmoil. The atmosphere is composed of over 96% carbon dioxide, with thick layers of sulfuric acid clouds that obscure the surface from view. The pressure is more than 90 times that of Earth, equivalent to being nearly a kilometer beneath the ocean. The heat reaches nearly 880 degrees Fahrenheit, 470 degrees Celsius. On Venus, metal melts in the open air. Spacecraft survive only minutes before being crushed or cooked into silence. But Venus may not have always been this way. Some planetary scientists believe it once had oceans, shallow seas that evaporated as volcanic eruptions filled the atmosphere with greenhouse gases. Without a stable magnetic field to shield it from solar radiation, Venus slowly lost its water to space. Hydrogen escaped into the void, while oxygen reacted with surface minerals, leaving behind a desert of superheated rock. Venus did not die in a sudden cataclysm. It transformed slowly, inevitably, over millions of years, proving that planets, like living creatures, can age and decay. The winds in Venus's upper atmosphere travel at hurricane speeds, circling the planet in just 4 Earth days. This phenomenon, known as superrotation, causes the clouds to race endlessly around the globe, driven by heat so intense that the very air seems to churn with desperation. Lightning flashes within the toxic storms. Acid rain forms in the clouds, only to evaporate before it ever reaches the ground. Even the word rain loses meaning on Venus. What falls from the sky never touches the surface. As we simulate what a human explorer would experience, we find that a step onto Venus would be a step into a furnace. The skies would be an unbroken orange haze. The horizon would shimmer with refraction from the searing heat. There would be no blue sky, no stars, only darkness and the distant outline of volcanic plains. Venus is home to more volcanoes than any other planet, perhaps over 1,600 major ones. Many still thought to be active. It is not merely hot, it is alive with internal fire, constantly reshaping its surface. Yet amidst this hostility lies a deeper truth. Venus is not just a failed planet. It is a mirror, showing us what can happen when a delicate equilibrium breaks. The same greenhouse effect that warms Earth to life has gone unchecked here, turning paradise into purgatory. In studying Venus, scientists gain insight into Earth's future. Venus is not our enemy, it is our warning. If life ever flickered here, it is gone now, erased by the relentless embrace of heat and pressure. Venus is a reminder that habitability is not guaranteed, that a planet's fate is written not just in its composition, but in its delicate relationship with its star. The time it takes to reach Venus is measured in months, but the time it takes to understand it may span generations. As we depart its orbit, we do so with a sense of reverent caution, aware that in Venus we have glimpsed a possible destiny we must strive to avoid. Mars beckons with its rusted deserts and whispering dust storms. Visible even to ancient eyes, the red planet holds our dreams of colonization. But how long until human boots leave the first footprints in its ancient sands? For centuries, Mars has called to us across the darkness, its red glow a constant reminder that another world lies just within our reach. Unlike Venus, which cloaks itself in secrecy, Mars offers its surface plainly to the cosmos, inviting us to study its canyons, valleys, and frozen polar caps. It is not just a planet, it is a possibility, a world that might one day cradle human life beyond Earth. To journey to Mars is to journey into our own future, a future where life becomes interplanetary. But Mars is not an easy neighbour to visit. Its orbit around the Sun is elliptical, sometimes bringing it within 34 million miles of Earth, and at other times, distancing it by more than 250 million miles. We cannot choose to leave whenever we want. Our departure must coincide with a cosmic rhythm known as the launch window, a moment that occurs roughly every 26 months, when Earth and Mars align on the same side of the Sun. In this narrow corridor of opportunity, the journey is fastest and requires the least fuel. When conditions are ideal, a spacecraft traveling on a Hohmann transfer orbit can reach Mars in approximately 6 to 9 months. This is not a straight path, but an elegant curve through the solar system, using Earth's momentum to carry the spacecraft outward until Mars's gravity catches it. During this time, astronauts would spend more than half a year drifting through deep space, further from home than any human has ever traveled. Day by day, Earth would diminish into a pale blue star until it appears no brighter than Venus does from our skies. The psychological journey, in many ways, is greater than the physical one. For the first time in human history, travelers to Mars would watch Earth become just another point of light in the universe. Communications would be delayed by minutes. Time would take on a different meaning, not measured in days or schedules, but in distance from home. Each moment would be accompanied by the knowledge that returning is not immediate, that every mile forward is a mile deeper into the unknown. As the spacecraft approaches Mars, the planet gradually grows from a red dot into a glowing orb. Its rusted plains and ancient riverbeds reveal themselves through swirling dust storms. The thin atmosphere, less than 1% as dense as Earth's, provides almost no protection from the harsh radiation of the sun. Yet below that dusty veil lies a world that once flowed with water, where ancient oceans may have stretched across its surface, where life may have once taken root. To reach Mars is to stand at the threshold of two great questions. Could life exist beyond Earth? And could humans one day thrive here? The first step onto Martian soil would not just mark the beginning of planetary exploration, it would signal the beginning of our evolution as a multi-planetary species. And while the journey may take only months, the meaning of that journey stretches across the entire span of human history. Mars is not just in reach, it is our next great chapter, waiting patiently in the red twilight of space. Reaching Mars isn't a straight line, it is a dance of orbital alignment. We explore how the perfect moment can shave months off our journey, and how missing it could add years. In space travel, timing isn't just important, it's everything. As Earth and Mars race around the Sun at different speeds, the distance between them is constantly changing. There are moments when the two planets line up in just the right configuration, creating a kind of cosmic doorway. If a spacecraft is launched during this precise window, it can glide efficiently along a curved path called a Hohmann transfer orbit, using minimal fuel while still gaining the maximum gravitational assist from the Sun. But if we miss this opening, the door closes, and the opportunity vanishes for nearly 2 years. Think of Earth and Mars as two runners on separate tracks. Earth is on the inner lane, moving faster. Mars is on the outer one, moving slower. In order to intercept Mars, we must leave Earth at exactly the moment when Mars is just ahead of us in its orbit. If we leave too late, we'll arrive where Mars was, not where it is. The universe does not wait for us. Its motions are precise, predictable, and indifferent to our schedules. We must align ourselves with the clockwork of the cosmos. These launch windows are calculated years in advance, down to the minute. Mission designers simulate planetary positions with powerful computers, predicting where Earth and Mars will be, not just months from now, but decades, or even centuries into the future. A launch mistimed by even a few days can require thousands of extra pounds of fuel, slowing the craft or causing it to miss Mars entirely and drift endlessly through space. But launch windows are only one part of the story. Gravity assists, or gravitational slingshots, allow spacecraft to steal energy from planets in motion. When a spacecraft flies close to a planet, it falls into its gravitational well, accelerates, and then exits on a different trajectory with extra speed. This maneuver doesn't cost fuel. Instead, it draws energy from the planet's own orbital momentum. The planet slows down ever so slightly, an imperceptible fraction, but the spacecraft gains a dramatic boost. The Voyager missions are perhaps the most famous example of this cosmic choreography. Thanks to a rare alignment of the outer planets that occurs only once every 176 years, Voyager 1 and Voyager 2 were able to hop from Jupiter to Saturn, then onward to Uranus and Neptune, using each planet as a stepping stone. Without gravitational slingshots, such a mission would have taken decades longer and required fuel tanks larger than the spacecraft itself. This is the invisible art of space travel, riding the gravity of planets like a surfer rides a wave. Space is not empty. It is filled with motion, with momentum, with energy waiting to be borrowed. By aligning our spacecraft with these forces, we transform the impossible into the achievable. Imagine watching Mars rise through the spacecraft window. Not because we forced our way toward it, but because we allowed the universe to carry us along its natural paths. Space exploration is not about conquest, it is about cooperation with celestial mechanics. The planets set the tempo, the sun keeps the rhythm, and we must learn to move in harmony with them. In the end, the question is not just how far Mars is, but when Mars is where we need it to be. The journey to other worlds depends not only on technology, but on timing, waiting for gravity to open its hand and guide us forward through the grand and silent corridors of space. Between Mars and Jupiter lies a realm of ancient stone. It is not the chaotic field of movies, but a sparse museum of planetary fragments. As we cross, we measure the time since the birth of the solar system itself. The asteroid belt stretches across hundreds of millions of miles, a vast ring of rocky remnants that once might have formed a planet. Instead, the immense gravitational pull of Jupiter prevented these fragments from ever coalescing into a world. Today, they drift silently through space. Relics from a time when our solar system was still forming, unfinished pieces of a cosmic puzzle. As we cross this region, the journey becomes less about reaching a destination and more about traveling back in time to witness the earliest building blocks of planets like Earth. Contrary to dramatic portrayals in science fiction, these asteroids are not clustered tightly together. Space between them is so vast that a spacecraft could pass through the belt without ever encountering a single rock. On average, objects within the asteroid belt are separated by hundreds of thousands of miles. In many ways, the greatest danger here is not collision, but isolation. The silence is profound. There is no air, no wind, no sound. Only the distant glimmer of ancient stones rotating slowly in the blackness, each one a witness to billions of years. As we travel deeper into this region, it becomes clear that the belt is not a graveyard, it is a library. Each asteroid is a page in the story of planetary evolution, preserving minerals, metals, and ice unchanged since the dawn of our solar system. Some are rich in water bound within their minerals, offering potential resources for future missions. Others contain rare metals in concentrations far greater than anything found on Earth. In the far future, humanity may look to this region for sustainable off-world mining, transforming these silent stones into stepping stones for interplanetary civilization. Time itself feels different here. There is no day or night, no rising or setting sun, only an unchanging panorama of stars. The only passage of time is the gradual shifting of the sun's light as our spacecraft continues its journey outward. In ancient times, the belt was a cradle of possibility. Now, it is a quiet threshold, a boundary between the familiar inner planets and the vast, mysterious outer realms. We pass by Ceres, the largest object in the asteroid belt, once classified as a planet in its own right. At nearly 600 miles across, it is a dwarf planet with water ice beneath its crust and mysterious bright spots that reflect the light of the distant sun. Some scientists believe that beneath its surface could lie a hidden ocean, perhaps even the ingredients for life. Other asteroids, like Vesta, reveal signs of ancient volcanic activity, hinting at a time when these bodies were not cold and dormant, but alive with internal fire. Crossing the asteroid belt is a journey that takes months, even at immense speeds, yet the true distance is not measured in miles, but in moments of reflection. These drifting stones remind us that we are part of a dynamic system, one that has evolved, collided, and transformed over eons. Earth and Mars, Venus and Mercury, these planets are complete chapters. The asteroid belt is an unfinished sentence, a celestial pause in the great story of our solar system. As we leave this region behind, we are no longer just travelers, we are historians of the cosmos, carrying with us the knowledge that every grain of dust here is older than life itself. Ahead of us lies Jupiter, the first of the gas giants, and with it, a new chapter of the journey, one not built of stone and silence but of storms and swirling clouds larger than entire worlds. Jupiter looms in the darkness, a world so massive it bends time around it. A journey here stretches our imagination of distance. What would it truly feel like to approach a planet deeper than all the oceans of Earth combined? As we leave the asteroid belt behind, the clock of our journey begins to tick differently. Every mile now places us deeper into the dominion of Jupiter, the largest planet in our solar system and the ancient guardian of our cosmic neighborhood. Its presence is unmistakable. Long before we see Jupiter with our eyes, we feel it in the instruments aboard the spacecraft. Gravity begins to shift. Space itself seems to curve toward an unseen colossus. This is no ordinary destination. This is a journey into the realm of giants. Reaching Jupiter is a monumental endeavor. Depending on the trajectory and technology used, a spacecraft can take anywhere from 13 months to nearly 6 years to arrive. For example, NASA's New Horizons probe, one of the fastest objects ever launched, reached Jupiter in just over a year. Meanwhile, other missions like Galileo and Juno took a longer route, using gravity assists from inner planets to gain the velocity needed for precise orbital insertion. But regardless of the path, the moment of arrival is unlike any other in solar exploration. The instant when Jupiter's immense gravitational force takes hold, pulling the spacecraft into its sphere of influence. Jupiter contains more than twice the mass of all the other planets combined. It is not just a world, it is a failed star, a celestial embryo that never accumulated enough mass to ignite nuclear fusion. As we approach, its swirling bands of red, orange and gold begin to fill our view. Its storms, some larger than Earth itself, rotate with unending fury, fueled by internal heat left over from its formation. Here, gravity is not just a force, it is an experience. Time itself dilates slightly in Jupiter's presence. Seconds pass just a little differently, a subtle reminder that we are now under the influence of a planetary titan. In the darkness of space, Jupiter glows faintly from the heat rising within. Unlike Earth, which warms itself with sunlight, Jupiter radiates more energy than it receives, powered by the slow gravitational compression of its massive body. As we draw closer, we see that its clouds do not drift placidly. They churn, they spiral. They rise and fall in colossal waves, forming structures so vast they defy comprehension. The Great Red Spot, a storm that has raged for centuries, spins like a blood-red eye watching the solar system unfold. The journey here is not just measured in distance, but in awe. Our perception of scale begins to dissolve. Jupiter's diameter is 11 times that of Earth. Its magnetic field is 20,000 times stronger. If we could hear electromagnetic waves as sound, Jupiter would roar with an ancient cosmic thunder, echoing across the void. And yet, despite its immense mass, Jupiter has no solid surface. To reach its center is to journey through layers of gas, liquid hydrogen, metallic hydrogen, each layer more extreme than the last, until matter itself becomes something alien and unknown. Even as we approach the orbit of its moons, the journey continues. Europa, Ganymede, Io, and Callisto drift around Jupiter like miniature planets, each with their own secrets. Some are volcanic, some are icy, some may harbour oceans beneath their crusts, oceans that could cradle life in the dark. The time it takes to reach Jupiter is not just a countdown, it is a transition from the familiar inner solar system to the vast, mysterious outer expanse, where planets are no longer rocky worlds, but entire systems within themselves. To journey to Jupiter is to stand at the threshold of the great beyond. It marks the moment when our voyage is no longer just about exploration, but about encountering forces so great they reshape our understanding of what a planet can be. Here, in the shadow of giants, time stretches, gravity deepens, and the universe reveals its true scale. No spacecraft truly visits the outer planets without first dancing around Jupiter's orbit. We explore how gravity itself becomes an engine, hurling us deeper into the void. Jupiter is not just a destination, it is a gateway. Its immense gravitational pull acts as a cosmic slingshot, capable of accelerating spacecraft to speeds that would otherwise be impossible with fuel alone. As we approach this planetary giant, we are not merely observers of its majesty, but participants in a celestial maneuver so elegant and powerful that it has enabled humanity to reach the farthest edges of our solar system. Harnessing Jupiter's gravity is not about resisting the planet's pull, but surrendering to it, allowing gravity to guide our trajectory and transform our speed with the precision of an ancient clockwork. A gravity assist, or slingshot maneuver, is one of the most ingenious strategies ever developed in space exploration. The concept is simple but profound. As a spacecraft approaches Jupiter, it falls into its gravity well, accelerating as it is pulled toward the planet. Instead of crashing into the massive sphere, it arcs behind Jupiter, catching a fraction of the planet's forward momentum as it orbits the Sun. This exchange is subtle, imperceptible to Jupiter but monumental to the spacecraft. With no fuel expended, the spacecraft is suddenly traveling faster, propelled outward on a new trajectory, often towards Saturn, Uranus, Neptune, or even beyond the edge of the solar system itself. This method was famously used by both Voyager 1 and Voyager 2. Launched in 1977, these spacecraft were designed to take advantage of a rare planetary alignment that occurs only once every 176 years. By precisely timing their journey and using Jupiter's gravity, they gained enough speed to visit all 4 outer planets in a single mission. Without the slingshot effect, reaching Neptune alone would have taken more than 30 years. Gravity became a silent engine, one that required no fuel, no maintenance, and has continued to propel Voyager 1 into interstellar space, where it now travels among the stars. As our spacecraft prepares for this maneuver, every movement must be calculated with extraordinary precision. If we pass too close to Jupiter, the intense radiation belts could damage or destroy the spacecraft's instruments. If we pass too far, we won't gain enough speed. The ideal trajectory is razor thin, measured in millimeters over millions of miles. Here, timing is not just important, it is absolute. The universe gives us a single chance to catch Jupiter's momentum. Miss it, and the journey may be delayed by decades. The experience of harnessing Jupiter's gravity is unlike any other. From our vantage point inside the craft, the giant planet grows rapidly in the window, its swirling clouds stretching across our entire field of view. We feel the gravitational pull increase. Even though gravity cannot be felt directly, its effects on acceleration become evident. Our onboard clocks begin to tick slightly slower due to time dilation caused by Jupiter's immense mass. We are not simply moving through space. We are moving through the contours of space-time itself. As the spacecraft swings behind the planet, Jupiter fills half the sky, glowing with storms that have raged for centuries. In that moment, we are suspended between two forces, the pull of Jupiter and the forward motion of its orbit. Then, with silent precision, we are flung outward. Our speed multiplies. Our path shifts. We are now no longer just visitors to the outer solar system. We are travelers of the deep beyond. Harnessing Jupiter's gravity is a reminder that space travel is not a battle against nature, it is a partnership with it. We do not conquer the cosmos by force, but by learning its rhythms, its patterns, its hidden pathways. Jupiter, the ancient king of planets, becomes our ally, opening the door to the solar system's farthest frontiers and sending us onward, toward the ice giants, the frozen moons, and secrets waiting in the darkness ahead. We draw closer to the Great Red Spot, an unending storm larger than our entire world. As the hours add up, we ponder, how long does it take not just to reach Jupiter, but to comprehend it? As our spacecraft settles into orbit around Jupiter, we enter the presence of one of the most enduring wonders of the solar system. The Great Red Spot is not merely a storm, it is a planetary monument to time itself. This colossal vortex has raged for at least 350 years, possibly far longer, swirling relentlessly within the planet's dense atmosphere. If Earth's fiercest hurricanes last days or weeks, the Great Red Spot is their ancient ancestor, spinning across centuries, untouched by landfall, uninterrupted by oceans, continuously fueled by the heat radiating from deep within Jupiter's core. From our vantage point high above Jupiter's cloud tops, the storm appears as an enormous oval, coloured in muted crimson and copper, circled by bands of white and tan that stretch around the planet like stripes on an infinite canvas. Lightning flashes silently in the swirling clouds, some bolts so powerful they could ignite entire cities. Winds howl at speeds over 400 miles per hour, faster than any storm ever recorded on Earth. And yet, in the stillness of space, we hear nothing. The storm is silent, its fury expressed only in motion. The Great Red Spot is so large that 2 or even 3 Earths could fit inside it. Observations across decades have revealed that the storm is slowly contracting, becoming taller and more circular as it ages. Some scientists wonder, is the Great Red Spot dying? Or is it evolving, preparing to transform into something we cannot yet imagine. A storm that lasts centuries may be as fleeting as a raindrop in Jupiter's vast atmospheric cycle. As we analyze the storm, instruments detect that it extends deep below the visible cloud tops, possibly hundreds of miles into the planet's interior. Unlike storms on Earth, which are powered by the sun's energy, Jupiter's storms are driven by internal heat. The planet is still contracting under its own gravity, releasing energy that fuels atmospheric motion from the inside out. The Great Red Spot is not just a weather system, it is a window into Jupiter's living, breathing interior. We observe how surrounding jet streams swirl around the storm, feeding it with continuous energy. Massive ammonia clouds rise and fall like ocean waves, while vortices spin off the storm's edges, only to be reabsorbed into the main vortex. The storm appears eternal, but it is constantly changing, its boundaries rippling like the edge of a flame. To truly comprehend the Great Red Spot is to accept the vastness of planetary time. On Earth, we measure time by hours, days, and years. On Jupiter, we measure it by storms that span generations. Storms that were raging before telescopes were invented, before electricity was discovered, before modern nations were born. To imagine standing above the storm is to imagine watching not just weather, but history itself in motion. The red spot forces us to ask profound questions. What does it mean for a storm to live longer than civilizations? What can we learn from a world where the weather is measured not in forecast cycles, but in epochs? As we drift past the storm, its presence lingers in our minds long after it fades from view. Not just as a swirling tempest, but as a symbol of time beyond human comprehension. We leave Jupiter's orbit with a new understanding. In the grand scale of the universe, even storms are not events, they are eras. And this, the storm that has lasted centuries, is a reminder that some forces of nature are not merely experienced, they are endured. Farther still, Saturn rises like a dream sculpted from ice and light. Its rings stretch wider than Earth itself. Reaching this world tests the limits of time and human patience. As we leave the gravitational embrace of Jupiter, our spacecraft continues onward, journeying through a realm where sunlight is fading into a pale, distant glow. The darkness deepens, but ahead, something luminous begins to emerge, a delicate, shimmering halo suspended in space. Saturn, the jewel of the solar system, slowly reveals itself. Unlike any other planet, its beauty is immediate, undeniable, and otherworldly. The rings, made of countless shards of ice and rock, catch the faint light of the sun and scatter it in all directions, creating a cosmic crown that glitters like frozen fire. Reaching Saturn takes time, years, not months. The fastest spacecraft ever sent to Saturn, NASA's Cassini, took nearly 7 years to arrive. Yet every day of travel is rewarded the moment Saturn comes into view. While Jupiter is massive and imposing, Saturn is graceful and enigmatic, a planet of golden hues, wrapped in veils of methane clouds and encircled by rings that stretch up to 175,000 miles from edge to edge. Despite their grandeur, these rings are incredibly thin, no thicker than a few dozen feet in many places. A planet-sized masterpiece, sculpted with the precision of a single brushstroke of cosmic art. Saturn is a world of paradoxes. Though it is the second largest planet in our solar system, it is the lightest by density. If there were an ocean large enough, Saturn would float upon it. Its winds howl across the atmosphere at speeds exceeding 1,100 miles per hour, faster than hurricanes on Earth. Yet the planet exudes a calm, ethereal presence, seemingly untouched by time. Saturn does not rage like Jupiter. It revolves in silence, its rings gently spinning like the slow hands of a celestial clock. As we approach, we notice that Saturn, like Jupiter, radiates more heat than it receives from the sun. Deep beneath its swirling clouds lies a core of rock and ice, surrounded by layers of liquid metallic hydrogen that churn and generate a magnetic field. Saturn's magnetic field is weaker than Jupiter's, but still powerful enough to trap charged particles and create auroras at its poles, brilliant light shows that dance through the planet's upper atmosphere, painting its night sky with ribbons of green and blue. But it is the rings that capture our attention most. They are not a single structure, but thousands, perhaps millions, of individual ringlets, each made of ice particles ranging from the size of grains of sand to that of entire mountains. These particles collide, fracture, and reform, guided by Saturn's gravity and the influence of small shepherd moons that carve gaps and waves into the rings, like celestial artists sculpting patterns in dust and ice. The rings are ancient, yet not eternal. They may be slowly dissolving, falling into the planet like a rain of ice. To see them is to witness a cosmic phenomenon in transition. Saturn's moons add yet another layer of mystery. Titan, with its thick atmosphere of nitrogen and lakes of liquid methane, challenges our definition of what a habitable world can be. Enceladus, a small icy moon, hides a subsurface ocean that vents water vapor into space from geysers at its southern pole. These moons remind us that even in the cold outer reaches of the solar system, warmth and potential life may still persist. To reach Saturn is to enter a dreamscape suspended in darkness. It challenges our perception of space not as empty, but as full of wonders waiting in the silence. The time it takes to get here is not a delay, it is part of the experience, a slow unfolding of the universe's grandeur. For Saturn is not merely a planet to be reached, but a moment in our journey when time itself seems to pause, allowing us to marvel at the delicate beauty of a world that could only exist in the vast stillness of space. As we drift through Saturn's rings, time seems to stop. Particles of ice drift silently, some older than humanity itself. Each moment becomes a meditation on age and distance. Gliding into the orbit of Saturn's rings is like entering a cathedral carved of ice and light. There is no sound, no wind, no atmosphere to disturb the stillness. Each fragment, whether the size of a grain of dust or a mountain, floats in its own quiet rhythm, locked in a delicate balance between gravity and momentum. The rings spin in flawless harmony, each particle following a path set in motion billions of years ago. In this region, time is not measured in seconds or minutes, but in revolutions, each orbit a silent echo of ancient cosmic history. As our spacecraft glides above the rings, we see that they are not a single structure, but a vast collection of ringlets, some thin as ribbons, others wide as continents. Yet most are astonishingly thin, no more than 30 feet deep in places, despite stretching hundreds of thousands of miles across. Their composition is deceptively simple, ice and rock, but these frozen particles are more than frozen debris. They are remnants of a moon that never was, or perhaps the shattered remains of one that once orbited Saturn before being torn apart by gravity. The rings reflect almost all the light that touches them. Even though Saturn is nearly 1 billion miles from the Sun, the rings shine with ethereal brightness, casting pale reflections onto the planet's clouds below. From our vantage point, the Sun glows as a distant star, and the light it casts turns the ice into a shimmering sea of diamonds. Each fragment spins independently, glistening, sparkling, and yet maintaining perfect order. Time stretches differently here. There is no sunrise or sunset within the rings, only an endless glow of refracted sunlight. If we were to reach out and touch one of these icy fragments, we would be touching a relic of primordial time. Some of these particles may be as old as the solar system itself, unchanged, untouched, drifting through ages while civilizations rise and fall billions of miles away on Earth. Between the rings exists space so vast that a spacecraft could pass through without ever colliding with a single particle. But these gaps are not empty. They are shaped by gravity, sculpted by Saturn's moons which act as shepherds. Tiny moons like Pan and Daphnis carve lanes through the rings, pulling particles inward and outward, maintaining the sharp boundaries between each section. This celestial dance is not random. It is a living system, constantly shifting yet eternally balanced. As we drift closer, we observe subtle waves rippling across the rings, caused by meteoroid impacts or gravitational resonances. These waves move slowly, like tides on an invisible ocean. Each oscillation reminds us that these rings are not static. They breathe with the rhythms of the solar system, rising and falling in time with the pull of gravity and the passage of ages. In the shadow of Saturn, time becomes contemplative. It is easy to imagine the rings as the universe's great timekeepers, each orbit a tick of a clock too vast for human minds. Here, between ring and ring, between ice and light, we are offered a rare gift, a pause in the journey. A moment to simply exist in the silence. Drifting through Saturn's rings is not just a voyage through space, it is a journey through time itself, a reminder that the universe is old, enduring, and patient. The rings may one day dissolve, falling slowly into the planet they orbit. But in this moment, suspended among them, we witness a frozen eternity, an ancient lullaby whispered across 1 billion years. Saturn's moon Titan has rivers that flow beneath alien skies. But how long would it take to stand upon its shores? And what would time feel like beneath a sun so dim it barely casts a shadow? Titan rises through Saturn's hazy glow like a world imagined in a dream. Wrapped in a thick orange atmosphere, it is the only moon in our solar system with weather, rivers, rain, and lakes, but not of water. Here, methane flows as liquid. It rains methane from clouds. Lakes lap against icy shores in cycles that mirror the hydrological rhythms of Earth. Though on Titan, everything is slower, colder, and stranger. Standing on Titan is not like standing on any world we know. It is stepping into an echo of what early Earth may have looked like, before life began, before oxygen filled the skies. And the time it takes to reach this world reflects its remoteness, both in space and in spirit. Our journey to Titan begins with orbital capture around Saturn. From here, it takes weeks to carefully descend toward the moon's orbit, adjusting speed and trajectory to penetrate its dense atmosphere. Titan orbits Saturn once every 16 Earth days, slowly rotating beneath the dim sunlight. A spacecraft descending through its clouds would take hours to reach the surface, passing through layers of organic haze that scatter sunlight into a perpetual twilight. Here, a single day lasts the equivalent of 16 Earth days. Night is not a moment, it is an era. When sunlight reaches Titan, it is gentle, filtered, and weak, about 1% as bright as on Earth. Yet this dim world holds incredible secrets. Lakes of liquid methane and ethane glisten like mirrors beneath orange skies, fed by rivers that carve valleys and deltas. Winds sculpt dunes of hydrocarbon sand. The surface temperature is a frigid negative 290 degrees Fahrenheit, cold enough to freeze water into rock-hard ice that forms the very bedrock of the land. Here, water behaves like stone, while methane behaves like life-giving rain. Time seems slower on Titan. The thick atmosphere muffles sound. Movements feel heavy, dreamlike. Gravity is only 14% that of Earth, allowing a human explorer to take bounding steps, drifting gently back to the surface. A minute stretches into a moment of wonder. A day feels like a month. Beneath the haze, Saturn's rings are often hidden, but sometimes, through breaks in the clouds, they appear as ghostly arcs in the sky, reminders that this world is part of a much larger celestial symphony. Yet beneath Titan's frozen surface, scientists believe a vast subsurface ocean of salty water may exist, kept liquid by internal heat. This ocean could be one of the most promising environments for life beyond Earth. Methane lakes above, water ocean below, Titan stands as a bridge between what we know and what we hope to find. The journey to Titan may take 7 years or more from Earth, but it leads us to a world that blurs the boundaries between the familiar and the alien. What makes Titan extraordinary is not simply its distance from us, but its similarity. It is a world with cycles, rain, evaporation, flowing rivers, seasons. But everything is transformed, shifted into another register of nature. Visiting Titan is like watching Earth's reflection through the mirror of time. Not our past, not our future, but something parallel, something possible. And so we drift above its surface, thinking not of how long it took to reach this moon, but of how long it has waited for us, quietly orbiting in shadow, keeping its secrets in liquid lakes and icy stones. In the silence, we realize Titan does not just challenge our understanding of planets, it challenges our definition of life itself. Now the distances grow vast. Our spacecraft enters a kind of hibernation as years pass in the silent drifting between orbits. Uranus awaits, a pale blue world tilted like a fallen compass. Beyond Saturn, a profound stillness takes over. The sun shrinks to a distant lantern, its warmth too faint to sustain solar-powered systems alone. Here, our journey becomes a test not of speed but of endurance. The path to Uranus is long, typically taking 7 to 10 years even with gravity assists. During much of this time, a spacecraft moves silently, systems powered down to preserve energy, instruments entering sleep cycles. It is a voyage through deep time, where days blur into months and months into years. Each moment becomes a gentle drift through the void, our craft a lone traveller in the cosmic dark, following a trajectory set in motion long ago. Uranus is unlike any other planet in our solar system. While most planets spin upright or slightly tilted, Uranus lies nearly on its side, its axis tipped by 98 degrees. This gives it the strangest seasons imaginable. Each pole spends 42 Earth years in continuous daylight, followed by 42 years of uninterrupted night. Imagine a world where winter lasts longer than a human lifetime, and sunrise comes but once every 4 decades. It is a planet of extremes, not in heat or storm, but in time itself. As our spacecraft approaches, its speed gradually decreases. The gravitational influence of Saturn fades behind us, and Uranus begins to assert its presence, a silent giant composed mostly of icy materials like water, ammonia, and methane. Unlike Jupiter and Saturn, which are gas giants, Uranus is classified as an ice giant. Its atmosphere is thinner, its layers denser, its composition more mysterious. The methane in its upper atmosphere absorbs red light, giving the planet its characteristic pale blue glow, a glow that seems to pulse softly in the darkness, like a sleeping world awaiting its next awakening. To reach Uranus requires not just distance, but precision. The planet orbits more than 1.8 billion miles from the Sun. Communications from Earth take nearly 3 hours to arrive. A single course correction could take days to verify. Navigation becomes less about active control and more about trust. Trust in the mathematics, in the gravitational models, in the subtle push of cosmic forces guiding the spacecraft forward. During this long journey, we are forced to contemplate time in a new way. A mission to Uranus spans generations of planning, engineering, and waiting. By the time the spacecraft arrives, the team that launched it may have aged, retired, or even passed away. The mission becomes larger than any one person. It becomes a gift from one era of humanity to the next, a message sent into the future, carrying our curiosity across decades. As Uranus comes into full view, we see a serene, ghostly planet, with faint rings and a family of moons that glide in tilted orbits, just like their parent world. These moons, such as Titania and Oberon, may harbour oceans beneath their icy crusts, making them potential havens for life. Winds whip through Uranus's upper atmosphere at speeds of over 500 miles per hour, whispering across a world with no solid surface, only layers of gas and ice, compressing gradually toward a core we still do not fully understand. In the silence of space, the journey to Uranus becomes something more than travel. The long sleep is not a pause in our journey, it is a reminder of how immense our cosmic neighbourhood truly is. And as our spacecraft awakens from its hibernation to greet this sideways world, we are reminded that even in the coldest reaches of space, there are still wonders waiting, silent, patient, eternal. On Uranus, a single season can last 21 Earth years. We measure not only the time to arrive, but the time to see a sunrise across a planet where dawn itself moves slower than any human lifetime. Imagine standing on a world where the concept of morning and evening is stretched beyond comprehension. On Uranus, sunrise is not a moment, it is an era. Instead of a gentle transition across the sky, the sun crawls slowly upward, barely shifting in position over the span of decades. Uranus is tipped so far on its side that its poles are almost directly pointed toward and away from the sun throughout its orbit. This creates seasons unlike any other in the solar system. Entire hemispheres spend more than 2 decades locked in constant sunlight, followed by more than 2 decades of unbroken darkness. To us on Earth, a season is a passing phase, a change we can observe over months. On Uranus, a season is a lifetime. If a child were born at the beginning of a Uranian spring, they would reach adulthood before summer arrived. If they lived to old age, they might still never witness the complete turn of all 4 seasons. A single Uranian year lasts 84 Earth years. Spring, summer, autumn, winter, each stretches the limits of human perception. As our spacecraft orbits high above the planet, we watch the sunlight pour across its pale blue atmosphere like a slow wave. The boundary between light and shadow, known as the terminator, barely moves. Day and night do not alternate in cycles of hours, but in ages. The slow rotation of Uranus, combined with its extreme tilt, means that one hemisphere lives under the constant gaze of the sun, while the other is plunged into deep, icy darkness. This unchanging illumination has a profound effect on the atmosphere. Winds build steadily for years without interruption, circling the planet in stable yet powerful bands. Though Uranus appears calm from afar, it is home to fast-moving storms and jet streams that rage silently across its upper layers. These storms grow stronger as one hemisphere shifts from light into darkness, reacting dramatically to changes in solar heating. For years, energy builds quietly in the atmosphere. Then, when the planet reaches equinox and sunlight begins to fall evenly across its equator, that built-up energy is released, triggering massive storm systems that flash across the planet's surface like celestial awakenings. The moons of Uranus experience these extreme seasons as well. As they orbit the tilted planet, their surfaces pass in and out of sunlight over decades, triggering cycles of freezing and thawing that may affect subsurface oceans. Some moons, like Miranda, bear immense cliffs and ridges, evidence of geological upheavals that may be tied to these long cycles of warming and cooling. In this part of the solar system, time is not a simple measure. It is a force, shaping the very surfaces of worlds. Imagine sleeping under Uranus's sky with years of twilight stretching endlessly across the horizon. There would be no quick sunsets, no fleeting nights. Instead, the sky would change at a glacial pace. Each fraction of movement, a reminder of the vast scales on which the universe operates. Seasons here are not simply weather, they are epochs. To understand Uranus is to step outside the boundaries of human time. It is to realize that our clocks and calendars, so important to us on Earth, are meaningless in the grand architecture of the cosmos. The journey to Uranus may take years, but truly knowing Uranus would take generations. In this world of eternal dusk and unending dawn, time itself becomes the landscape, and we are but momentary visitors in an ancient and silent cycle. At the edge of the gas giants lies Neptune, a world of sapphire winds faster than any storm on Earth. To reach it is to step outside of ordinary time. The journey to Neptune is not a voyage measured in days or even months. It is measured in years, decades, and generations of curiosity. It is the farthest known planet from the Sun, orbiting at a distance of nearly 2.8 billion miles from Earth. Once we set our course beyond Uranus, the darkness grows more profound, the light more distant, and a strange transformation takes place. Time seems to dissolve. There are no markers of day and night here, only the distant gleam of stars that no longer twinkle. The sun becomes no larger than a bright star itself, a pinhole of light in an ocean of night. To travel toward Neptune is to drift toward the threshold where our familiar concepts of time and distance begin to unravel. Spacecraft traveling to Neptune rely on gravity assists, typically from Jupiter or Saturn, to accelerate them outward. Even with these celestial slingshots, it can take 12 years or more to arrive. Voyager 2, the only spacecraft to ever visit Neptune, launched in 1977 and reached Neptune in 1989, a span long enough for a child to grow into adulthood. That is the scale of the outer solar system. Every moment out here is magnified. Every mile stretches the journey not just through space, but into deep time. As we approach Neptune, we behold a world unlike any we have encountered. Though it is classified as an ice giant like Uranus, Neptune is far more dynamic and mysterious. Its atmosphere churns with storms that dwarf Earth itself. Winds here can reach speeds of over 1,300 miles per hour, the fastest in the solar system. These winds howl through the methane-rich skies, giving Neptune its deep blue hue, as if the planet itself were a storm captured in eternal motion. Time blurs not simply because of the distance, but because of Neptune's alien nature. A single day on Neptune lasts just 16 Earth hours, yet a Neptune year spans 165 Earth years. Every storm that forms here could last longer than a human lifetime. Every season takes decades to unfold. If you were to stand on one of Neptune's moons and watch the planet rise above the horizon, you might witness the same storm for the duration of your entire life, with no guarantee it would end even then. Beneath Neptune's clouds lies a mantle of exotic ices, water, ammonia, and methane compressed into a superfluid state unlike anything found on Earth. Deeper still, scientists believe there may be an ocean of superionic water, where hydrogen ions move freely through a lattice of oxygen atoms, an ocean that conducts electricity and generates the planet's powerful magnetic field. Lightning may flicker through these hidden depths, never reaching the surface, trapped within layers of unimaginable pressure. Orbiting Neptune is Triton, one of the most unusual moons in the solar system. It orbits backwards, opposite Neptune's rotation, suggesting it may be a captured object from the Kuiper Belt. Triton is geologically active, with geysers that erupt nitrogen ice into space, proof that even in this distant realm, worlds are still alive with motion. Here, the past and present collide. Triton may be a preview of Pluto or a relic from the solar system's earliest days. To reach Neptune is not simply to arrive at a planet, it is to stand at the frontier of our solar system's story. Beyond this point lies only darkness, cold, and the faint whisper of the sun's fading breath. Neptune reminds us that we live in a universe vast beyond measure, a universe where time and distance are not barriers but teachers. It is here, in the sapphire depths of Neptune, that time begins to blur, and our journey turns from exploration to wonder. Storms race around Neptune in an endless ballet. We imagine entering this world's orbit and watching wind carve patterns across eternity. As our spacecraft slips into the gravitational embrace of Neptune, we are greeted not by a silent, frozen void, but by motion, pure, ceaseless, breathtaking motion. Neptune may be the farthest planet from the Sun, but it is anything but still. It is alive with wind. Its deep blue atmosphere churns in massive belts, storms erupt and vanish like thoughts in the mind of a dreaming world, and winds howl at speeds faster than sound. This is not simply weather, it is symphony. A haunting, hypnotic song made not of sound, but of motion, light, and time. Unlike the gas giants Jupiter and Saturn, Neptune's dynamic weather patterns are driven not by sunlight, which is faint and distant, but by internal heat. Neptune radiates more than twice the energy it receives from the Sun, suggesting an unseen furnace within, a hidden force stirring its skies into perpetual dance. As we peer down through its upper clouds, we begin to see how this energy rises upward, fueling storms that span entire hemispheres. The winds, invisible but relentless, shape the clouds into smooth bands, spiraling vortices, and waves that ripple across the planet like breath on glass. The fastest winds in the solar system blow here, reaching speeds of 1,300 miles per hour. For comparison, the most powerful hurricanes on Earth rarely exceed 150 miles per hour. These Neptunian winds are nearly 9 times stronger, capable of moving with such intensity that they redefine our understanding of atmospheric motion. Imagine watching a storm that circles the entire planet in mere hours, moving so quickly that it appears almost frozen in shape, even as it tears through the upper atmosphere with unimaginable force. One of the most striking features is the Great Dark Spot, a colossal storm system first observed by Voyager 2 in 1989. Unlike Jupiter's ancient red spot, Neptune's storms appear and disappear over relatively short periods, lasting only years instead of centuries. Yet during their lifetimes, they dominate the atmosphere with powerful cyclones, bordered by high-pressure ridges that channel winds in vast circular flows. These storms do not vanish quietly. They evolve, migrate, and sometimes reappear elsewhere, suggesting deep atmospheric layers at work beneath the surface. But even in the midst of chaos, there is beauty. High-altitude clouds of methane ice drift across Neptune's skies, gleaming white against the planet's azure hue. These clouds form and dissolve in delicate patterns, like the brushstrokes of an artist painting in air. They cast shadows on the deeper clouds below, tracing the invisible pathways of the wind. From orbit, it looks like the entire planet is breathing. The soundless nature of it all adds to its surreal quality. There is no air for us to hear the roaring winds. There is no medium for sound to carry. If we were to lower a probe into Neptune's atmosphere, we would see motion but hear nothing, a silent storm unfolding in perfect stillness. It is a reminder that not all symphonies must be heard. Some are meant to be seen, felt, and understood across the vast distances of imagination. As we drift above Neptune's swirling bands, time seems to slow. The storms move in eternal loops, the winds brush the edge of space, and we are left with a profound realization. Even in the farthest reaches of our solar system, nature is still dancing. Neptune's winds are not a sign of violence. They are a celebration of energy, of motion, of a planet singing its own ancient song into the cosmos. In this deep blue symphony, there are no beginnings and no endings, only movement. A reminder that the universe is always alive, always in motion, always whispering its secrets through the silent currents of space. Beyond Neptune, the sun becomes a distant star, its wind weakens, the journey slows. We now travel through a realm where time seems to stretch infinitely. Here, at the outer edge of our planetary system, we begin to leave behind the comforting breath of our star. For all of Earth's history, the sun has exhaled a continuous stream of charged particles, solar wind, that flows outward in every direction, creating an invisible bubble known as the heliosphere. This protective cocoon has shielded our solar system from interstellar radiation, shaping the boundaries of our cosmic home. But now, as we push farther than Neptune's orbit, that bubble begins to thin. The solar wind loses strength, the influence of the sun's magnetic field diminishes, and with each passing mile, we step deeper into an ancient boundary zone where our star's dominion begins to fade. This region is known as the heliopause, the place where the solar wind collides with the interstellar medium, a sparse, cold fog of atoms and cosmic particles that fills the galaxy. Unlike the sharp borders of planets, this boundary is not a wall but a gradual blur. Our spacecraft detects fewer and fewer solar particles. In their place, higher levels of galactic cosmic rays begin to appear, radiation traveling from distant stars, supernovae, and cosmic events far beyond our solar system. Here, the sun is no longer the dominant presence, it is merely one star among billions. Time, too, begins to change in this place. With no gravitational wells to fall into, no orbital alignments to chase, our spacecraft coasts steadily into the great unknown. The journey becomes less a matter of arrival and more a meditation on endurance. It may take years, even decades, for a craft to cross this boundary. The The distances are so vast that conventional terms lose meaning. Billions of miles, hundreds of astronomical units, decades of travel, and still we are only at the edge of our neighborhood. As we drift onward, the sun's light continues to dim. At this distance, sunlight takes more than 4 hours to reach us and is as faint as moonlight on Earth. Solar panels would be useless here. Only nuclear-powered engines keep our spacecraft alive. There are no planets now, only the occasional comet, the frozen remnants of creation drifting endlessly in the void. The temperature around us drops near absolute zero. Yet, mysteriously, we begin to detect a boundary of warmth, a region known as the heliosheath, where the solar wind, slowing down, causes a buildup of heat as it presses against the interstellar medium. It is a final breath, a last whisper from our star, before its influence vanishes entirely. Beyond the heliopause lies true interstellar space, a realm untouched by any planetary influence. Only 2 human-made objects, Voyager 1 and Voyager 2, have ever crossed this frontier. Their signals take more than 18 hours to reach Earth. Yet they still speak. Faintly, their voices echoing across the darkness, reminding us that humanity has already extended a hand into the galaxy beyond. At the edge of the solar wind, we confront a profound truth. Our solar system is not a closed system, but part of a larger galactic ocean. The sun is not a center, but a single flicker in a vast tapestry of stars. And while the journey between planets can be measured in months or years, the journey beyond the heliopause stretches into cosmic time. In this realm, time is no longer a human construct, it is a fabric we drift across. A silent current pulling us toward the next great frontier. The edge of the solar wind is not an ending, but a threshold. Beyond this point lies the beginning of everything else. Pluto is no longer classified as a planet, yet it still calls to us. A frozen relic of creation, its journey is measured in decades, one spacecraft, one chance, one silent flyby. As we travel beyond Neptune's orbit into the dim outskirts of the solar system, we are drawn to a world once considered the 9th planet, a world of mystery and myth. Pluto, small and remote, drifts through the Kuiper belt like a solitary wanderer caught between eras. It is not a planet in the modern sense, but it is not merely a rock either. It is a preserved chapter of the solar system's earliest history, orbiting the sun in a long, stretched ellipse that carries it farther from home than any other major body ever classified as a world. To reach Pluto is to reach a frontier of knowledge, a place where the known universe gives way to the unknown, where questions begin to outnumber answers. The journey to Pluto is the longest interplanetary voyage humanity has ever attempted. New Horizons, the first and only spacecraft to visit Pluto, took 9.5 years to reach it, travelling at extraordinary speeds, crossing more than 3 billion miles. For nearly a decade, it coasted through darkness, a slumbering traveller guided by precise gravitational slingshots and carefully timed course corrections. There is no second chance. Once the spacecraft approaches Pluto, it cannot slow down. It must capture every image, every measurement, every reading in a matter of hours before it is flung onward into the deeper void forever. As we draw near, Pluto slowly comes into focus, not as a dull, dead rock, but as a breathtakingly complex world with glaciers of nitrogen ice, mountains of frozen water, and a thin, trembling atmosphere that expands and collapses with the seasons. The largest heart-shaped glacier on its surface, known as Tombaugh Regio, reflects sunlight with dazzling brightness, hinting at active geological processes. In the faint sunlight, Pluto glows softly, not with heat, but with quiet persistence. Time here flows differently. A single year on Pluto lasts 248 Earth years. A human being could not live long enough to see it complete one full orbit around the Sun. When New Horizons arrived in 2015, Pluto was still in the same season it was in when it was discovered in 1930, winter turning slowly toward spring. Seasons are not fleeting cycles, they are epochs that span generations. Orbiting Pluto is its companion Charon, a moon so large relative to Pluto that together they form a binary system, orbiting a point in space between them. Charon is a frozen world of deep canyons and fractured crust. In the distant sunlight, it appears as if carved from ancient ice, scarred by tectonic forces we cannot yet explain. This binary dance is slow, graceful, and eternal, a reminder that out here, in the deep, time stretches beyond imagination. And when our spacecraft performs its brief flyby, we are left with a sense of profound stillness. We cannot linger. We cannot. Pluto slips past us in silence, and we are propelled onward into the Kuiper Belt, a vast region of icy bodies, comets, and dwarf planets yet to be explored. This is where the solar system ends and the mysteries of interstellar space begin. Pluto is not simply an end, it is a threshold. It marks the dawn of the unknown, where our solar system fades into cosmic night. In reaching Pluto, we do not conclude our journey. We begin it anew, stepping beyond the realm of planets into the deeper story of our place in the universe. Out here, time is not measured in human years, but in the slow orbits of frozen worlds, in the quiet turns of stars, in the hush before discovery. And still, we go on. To reach the outer worlds in a human lifetime, we must consider something once only science fiction, sleeping through the decades. What does time become if you are not awake to witness it? As our journeys extend further into the solar system, time itself becomes the greatest barrier. Even at extraordinary speeds, missions to the outer planets can take decades. For a spacecraft, decades are manageable. Solar panels endure, nuclear batteries hum quietly, instruments sleep and awaken on command. But for a human being, decades are lifetimes. A journey to Neptune, Uranus, or beyond Pluto is not merely a trip, it is a commitment to vanish from Earth's timeline. By the time you return, if return were even possible, the world you left behind might be completely transformed. Friends gone, nations changed, history rewritten. And so the question arises, could we one day sleep through time? Cryogenic travel, the slowing or suspension of biological processes through extreme cold, is a concept born in the pages of science fiction but quietly pursued in modern laboratories. The idea is simple in theory. A human is put into a deep, regulated sleep, body functions reduced to the barest minimum, metabolism slowed to a near halt. In this state, aging could be drastically reduced, perhaps nearly paused. Days, months, even years might pass like moments. If perfected, cryogenic sleep could turn a 30-year journey to the outer solar system into what feels like a single night. Imagine drifting through space in a cryosleep chamber. Outside your window, Neptune glides silently across the stars, a luminous blue orb hanging in darkness. Inside, your heartbeat is slow, your breathing shallow. Your body is neither awake nor truly unconscious, but suspended, held in a kind of biological stasis, waiting for the moment of reawakening. Space becomes a dream you do not experience in real time. Scientists already use cryogenics to preserve cells, tissues, and organs. Frogs in polar regions freeze solid during winter, only to thaw and return to life in spring. Certain fish, insects, and microorganisms endure extreme cold in suspended animation. Nature has already solved this problem. It is up to us to learn. In the near future, experimental missions may attempt partial torpor, reducing astronaut metabolism by inducing deep sleep conditions, lowering body temperature just a few degrees. Even this could reduce food, oxygen, and water requirements by up to 75%, making long voyages far more feasible. A slow journey through the solar system becomes a shared dream among travelers, who awake only during critical mission phases. But cryogenic travel is not merely a technical challenge. It is a psychological frontier. What happens to the human mind when time is erased? When memory becomes a bridge between centuries, would sleep feel like a moment between breaths, or like stepping outside of existence, waking in a future where everything has changed? Time, in cryogenic travel, becomes elastic. It ceases to be something we experience. It becomes something we cross. The outer solar system, once unreachable, becomes accessible not by increasing speed but by surrendering to stillness. By sleeping through time, we redefine what it means to travel. The limits of a human lifetime dissolve. The universe opens. And in that quiet, frozen chamber, beneath the hum of life support systems, a new era begins, where distance is measured not in miles, but in dreams. Even at light speed, reaching some planets would still take minutes. We explore how even light must travel, and how time itself warps at extreme velocity. For all of human history, speed has been a measure of power, of freedom, of technological triumph. The horse, the steam engine, the jet, the rocket. Each breakthrough has brought us closer to the stars. Yet no matter how fast we go, one barrier looms over all others: the speed of light. At 186,282 miles per second, light can circle the Earth 7 times in one heartbeat. It is the fastest thing in the universe, the final speed limit for matter, energy, and information. And still, even light takes time. When we gaze at the planets in the night sky, we are not seeing them as they are now, but as they were seconds or minutes ago. Light from the moon takes just over 1 second to reach Earth. Light from the sun takes 8 minutes and 20 seconds. When we look at Jupiter, we are seeing it as it was nearly 35 minutes ago. Neptune, nearly 4 hours. Even the closest objects in space are already memories by the time their light reaches our eyes. So, what would a journey at light speed actually feel like? And how long would it take to visit each planet if we could ride a beam of light? To reach Mars at its closest approach, light takes about 3 minutes. But when Mars is on the far side of the Sun, light may take over 21 minutes. In a universe governed by relativity, time and distance are not constant. They stretch and bend depending on your frame of reference. Traveling near the speed of light would cause time to slow down for the traveler relative to those back on Earth. A journey of decades from Earth's perspective could pass in mere moments aboard the ship. Yet this extraordinary effect comes with equally extraordinary challenges. As an object accelerates toward light speed, its mass effectively increases, requiring exponentially more energy. To reach 99%, the speed of light would take an immense amount of energy, perhaps more energy than is available on Earth. At 100%, the equation breaks entirely. To accelerate a massive object to light speed would require infinite energy, and infinity is not a resource we can mine. Even light itself, massless, tireless, obeys the rules of time. It does not arrive instantly. It must traverse the immense spacings between planets and stars. Light from Alpha Centauri, our nearest neighbouring star, takes over 4 years to reach us. Light from the Andromeda Galaxy takes 2.5 million years. Every photon is a traveller on a journey, with a beginning and an end. The speed of light is not a convenience. It is a boundary, a fundamental feature of reality, woven into the very geometry of space-time. Einstein's theory of relativity tells us that as we approach light speed, not only does time slow, but the very fabric of space begins to warp. Distances shrink. Seconds stretch. The universe reshapes itself around the traveller. Light speed is not just a velocity, it is a horizon of experience, a threshold beyond which time and space cease to behave as we know them. Yet even if we cannot reach light speed, we can measure our dreams against it. We can ask, how long would it take light to reach the outer planets? To visit Pluto? To cross the heliopause and enter interstellar space? These times are not hours or days, they are reminders of the vastness of our cosmic neighbourhood. They reveal not our limits, but our scale. Because in the end, the speed of light is not the limit of our imagination, it is the measure of our wonder. From nuclear fusion to antimatter and beyond, we ask, what drives will shorten our journeys? What would it take to make Neptune a mere weekend trip? Humanity has always advanced by turning dreams into engines. Where imagination leads, technology eventually follows, and as we reach the limits of chemical rockets, The same basic propulsion we've used since the dawn of space exploration, we now look toward ideas that exist at the edge of science and speculation. Dreams that could one day transform centuries-long voyages into journeys that fit within a single human lifetime, or even a single year, a single week. What if distances that once defined the boundaries of human possibility became merely destinations in the sky, a matter of choice rather than fate? To unlock such dreams, we must first consider the technologies that could take us beyond our current limitations. Among the most compelling is nuclear fusion propulsion, which would harness the very reaction that powers the stars. Rather than burning fuel for thrust, fusion engines would combine hydrogen isotopes at intense temperatures, releasing energy millions of times more efficient than chemical fuel. If mastered, fusion propulsion could enable journeys to Mars in as little as 30 days, to Jupiter in a few months, and to the outer planets in under 2 years. The stars themselves would no longer be metaphors, they would be fuel. Then there is antimatter propulsion, the pinnacle of energy efficiency. When matter and antimatter meet, they annihilate each other, releasing pure energy as dictated by Einstein's famous equation E equals mc². A spacecraft powered by antimatter would need only milligrams of fuel to generate the energy of nuclear tons. Accelerations to significant fractions of the speed of light become possible. A trip to Neptune, currently measured in decades, might take weeks. Pluto, a destination at the solar system's edge, could become a stop on a routine survey route. But controlling antimatter is profoundly difficult. It cannot touch ordinary matter without instantly annihilating. It must be contained within magnetic fields, suspended in vacuum. Currently, all the antimatter humans have ever produced could barely power a light bulb for seconds. Yet the concept remains, waiting for a future when energy is no longer a resource to be consumed, but a force to be engineered. Beyond fusion and antimatter lies the frontier of light sails or laser propulsion. Instead of engines, a spacecraft equipped with a sail thinner than a human hair could ride beams of concentrated light produced by powerful lasers stationed near Earth. Photons exert pressure, and over time, without any fuel needed, could accelerate a craft to a significant fraction of light speed. The Breakthrough Starshot initiative proposes such a mission, aiming to reach Alpha Centauri in just 20 years. If we can travel to another star in decades, what might such propulsion do within our solar system? Mars could be hours away, Jupiter a day, Neptune a weekend journey. There are even wilder dreams. Warp drives, wormholes, space-time manipulation. These concepts arise not from fantasy, but from the mathematics of general relativity. In theory, space itself can expand faster than the speed of light. If a spacecraft could compress space in front of it and expand space behind it, it might move without technically breaking the cosmic speed limit. Reality may resist such an idea, but it does not forbid it outright. Every breakthrough begins as an impossibility. Once, heavier-than-air flight was impossible. Once, reaching orbit was a dream. Now, humans orbit Earth daily, probes travel billions of miles, and robotic emissaries have stepped beyond the solar wind. The dreams of tomorrow are not fantasies, they are preview sketches of our future history. Each propulsion idea, fusion, antimatter, light sails, is a whisper from the future, asking us only one question: how far do we wish to go, and how soon? At extreme speeds, time itself slows for the traveller. We explore how reaching distant planets could mean returning to an Earth that has aged beyond recognition. Imagine stepping aboard a spacecraft designed to travel near the speed of light, faster than any human has ever moved, pushed beyond the limits of ordinary physics into the realm of relativity. As the engines ignite and your ship begins accelerating toward a significant fraction of light speed, something extraordinary begins to happen. Not outside the spacecraft, but inside you. Time itself starts to behave differently. Seconds seem normal, minutes pass as usual, but the universe observes a different truth. From the perspective of those left on Earth, you are slowing down in time. This phenomenon is known as time dilation, predicted by Albert Einstein's theory of relativity. As you move faster, your experience of time contracts. A journey to Neptune, which might take 30 years according to Earth's clocks, could feel like only a few years, or even months, for you aboard the ship. Your heartbeat, your aging, your very thoughts would all occur at their normal rhythm. But outside, the rest of the universe would be racing ahead. To the traveler, the stars grow closer. To the observer, the traveler fades into the distance, their time stretched thin against the fabric of space. If you were to spend what felt like 5 years journeying to the distant edge of the solar system and back, you might return to an Earth 50 years older. Children you once knew would now be elders. Entire generations might have passed. You would be both an explorer and a time traveler, thrust into your own future. This effect is not merely theoretical, it has been measured. Astronauts aboard the International Space Station, traveling at high speeds relative to Earth, age microseconds slower than those on the ground. The difference is tiny, but undeniable. At relativistic speeds, those microseconds could become months, years, even decades. If a spacecraft could travel at 90% the speed of light, time aboard it would pass more than twice as slowly. At 99%, time would slow by a factor of 7. At 99.999%, which some advanced propulsion concepts theoretically allow, 1 year aboard the spacecraft could correspond to centuries passing on Earth. To the traveler, distance collapses. What once required lifetimes may now be experienced in moments. Space becomes navigable, planets become reachable, but time becomes the cost. As we accelerate into these futuristic realms, we are forced to confront a fundamental question. What is the true measure of travel? Is it distance or time? Is it how far we go or how much of ourselves we leave behind? In ancient myth, heroes journeyed to strange lands and returned to find their homes transformed, their names forgotten. Time dilation reveals that myth was a prophecy of physics. The faster we move through space, the slower we move through time. One day, human explorers may leave Earth knowing they will never truly return, not because they cannot make the journey back, but because the Earth they return to will not be the one they left. They will step out into the future as living artifacts of a past no one remembers. And yet, for many, the journey will be worth it, because to travel is to witness, to explore is to become part of the universe's unfolding story. Time dilation reminds us that the greatest distances are not just measured in miles but in moments. It is not merely space that separates us from distant worlds. It is time itself. From Earth to the Kuiper Belt, each step reveals a truth. Planets are not just destinations, but moments in time. Our journey maps not just space, but history. As our spacecraft drifts through the outer reaches of the solar system, beyond planets, moons, and frozen relics of the early universe, we begin to understand something profound. We did not simply travel outward, we traveled backward and forward through time. Each world we encountered served as a chapter in the cosmic story. Mercury, the scorched remnant of planetary formation. Venus, a cautionary tale of runaway transformation. Earth, a cradle of life and consciousness. Mars, a memory of what might have been. The giants, keepers of storms and gravity. The dwarfs, guardians of the outer frontier. What began as a journey through distance has become a journey through meaning. Perspective, out here, changes everything. From Earth, the night sky seems serene. But from the vantage point of deep space, we see the truth. Our solar system is not a static arrangement of planets, but a dynamic, evolving system of migrating bodies, frozen oceans, and silent storms, all bound together by the invisible threads of gravity and time. Each planet is not just a location. It is a record, a preserved state in the great unfolding of cosmic history. Looking back toward the inner solar system, the planets form points of light indistinguishable from stars. Earth, our home, our everything, is now no larger than a shimmering pearl glinting in the cosmic sea. In that single glimmer lies every human memory, every conflict, every triumph, every word ever spoken. All of history, contained in one fragile dot of light. This perspective is not humbling, it is awakening. It reminds us that the divisions we create on Earth are invisible from space. The borders we fight over, the arguments we hold on to, dissolve in the face of the universe's vast silence. And yet, this cosmic view is not a removal of meaning, it is an expansion of it. In seeing our smallness, we discover our significance, not in our size, but in our awareness. We are the universe contemplating itself. We are the first species, as far as we know, to measure the distances between the stars, to chart the movements of planets, to ask, how long would it take to reach them? And what would we find when we arrive? We are not lost in the scale of the cosmos. We are born for it. The cosmic perspective gives us a new understanding of time. The age of a storm on Jupiter, the freezing crawl of nitrogen across Pluto's heart-shaped plain, the whisper of the solar wind fading into interstellar space. Our journey has shown us that time is not a straight line. It is a tapestry, a fabric woven with the lifetimes of worlds, the orbits of moons, the dance of galaxies. As we hover at the edge of the solar system, on the cusp of darkness beyond our sun's reach, we realize this journey is not about reaching a final destination. It is about awakening to the fact that we are part of something vast, ancient, and beautiful. That Earth is not the center, but a beginning. A starting point for minds that dare to look outward and imagine what lies beyond. The cosmic perspective does not diminish our existence, it elevates it. For in the end, the measure of our lives is not how far we travel, but how deeply we understand where we are. And with this understanding, we turn toward the final horizon, where our solar system ends and the galaxy begins. As we look beyond Pluto toward the vast Oort cloud, we ask one final question. If it takes decades to reach the edge of our own solar system, what would it take to reach another sun? At the far edges of our solar system lies a boundary that is not marked on any map. It is a threshold between what belongs to our sun and what belongs to the galaxy. Beyond Pluto stretches an enormous spherical shell of icy bodies known as the Oort cloud, a silent reservoir of primordial material left over from the birth of the planets. It extends so far that even light, travelling at unimaginable speed, would take nearly a year to cross from one side to the other. To reach its outer edge would take a spacecraft tens of thousands of years. In this place, our solar system whispers its final farewell. The Oort cloud is not a single world, but a cosmic womb, home to trillions of icy objects, comets, and frozen relics that have never felt the warmth of the sun. They drift in darkness, suspended in a slow-motion ballet governed only by gravity. Occasionally, one is nudged inward by the passing gravity of a distant star, beginning a spiral that will take millions of years before it becomes a comet visible from Earth. These icy wanderers are messengers, from the edge of time, from the beginning of everything we know. The idea of reaching another star becomes both tantalizing and daunting. Even the closest star system, Alpha Centauri, lies more than 4 light-years away. Travelling at the speed of our fastest spacecraft today, it would take over 75,000 years to reach it. To send a message there and back would take nearly a decade, just for a reply. In the space between stars, there are no suns to guide us, no planets to slingshot around, only the thin breath of interstellar hydrogen and the faint dust left behind by ancient supernovae. Yet even here, in this abyss, hope persists. The universe is not empty, it is filled with destinations waiting to be discovered. Rogue planets may drift in the darkness, untethered from any star, carrying hidden oceans and unknown secrets. Brown dwarfs, star-like objects that never fully ignited, dot the interstellar void, glowing faintly with residual heat. And beyond them lie the stars themselves, billions of them, each with its own retinue of planets, moons, and mysteries. Standing at this final horizon, we realize that our journey through the solar system has been more than a travelogue, it has been training. A rehearsal for the next great adventure. Interstellar exploration. The questions we now ask are no longer, how long would it take to reach Mars? Or can we stand on Titan? They expand into deeper territory. Can we preserve consciousness across centuries? Can we build ships that become generational worlds? Can humanity evolve not just physically, but philosophically, for voyages that may never return? The edge of the solar system is not an ending, it is a beginning. A place where the light of our sun fades into the universal darkness, and where the dreams of humanity rise like new stars. For while it may take millennia to cross the Oort cloud, and millions of years to traverse the galaxy, time itself is not our enemy. It is our companion. Every world we reach, every mile we travel, is part of a much grander voyage, one not measured in generations or empires, but in the evolution of consciousness itself. We are not earthbound beings. We are not even solar beings. We are galactic in potential, woven into the very fabric of the universe. And as we drift beyond the final horizon, a new question calls to us through the silence. Where will we go next? As our journey comes to a gentle close, we find ourselves drifting in the serenity of the cosmic ocean, our spacecraft silent, the stars shimmering like distant memories against an infinite black canvas. We have travelled outward from our blue home, past worlds shaped by fire and ice, through rings of ancient light, across storms that have raged for centuries, all the way to the edge of our sun's final breath. What we discovered along the way is more than distance. It is perspective. Each planet we visited was not merely a destination, it was a chapter in time. Venus, a reminder of balance lost. Mars, a dream waiting to be awakened. Jupiter and Saturn, guardians of motion and gravity. Uranus and Neptune, quiet storytellers of cold and time. And at the solar system's edge, where even light hesitates, we stood at the doorstep of eternity. In this great voyage, we were reminded that Earth, our first home, is not small because it is one world among many, but precious because it is alive, because we are here. Because every planet we explored made one truth shine brighter, that life, consciousness, and wonder are the rare jewels of the universe. As you breathe now, slowly and softly, let your thoughts drift like stardust. Feel the peace of knowing you are part of this grand cosmic story, not separate from the universe, but woven into it. The atoms in your body were forged in ancient stars. The rhythm of your heartbeat echoes the turning of planets. You are not merely in the cosmos, you are the cosmos. Become aware of itself. So rest now, traveller of time and stars. Know that the universe is vast, and yet, in this moment, you are exactly where you are meant to be. Good night.